Hello, I'm Martin Looker. Welcome to this Silicon Labs Dev Lab. In this video, I'll walk you through the creation of a matter over thread device using Arduino's Nano Matter board that features Silicon Labs EFR32 MG24 multi-protocol microcontroller. The Silicon Labs core for Arduino already includes many different device types, and those that are not included, we're working to add. So for this video, I'm going to create a single physical device with two logical colour bulb endpoints. Normally in this situation, there'd be two independent lights, each displaying a different colour. But for this video, I'm going to create a plasma-like effect to generate a mood light showing colours between the two selected endpoints. There are plenty of resources and software used in this video, and you can find links in the video description. I'm going to be using an Amazon Echo Show 8 3rd generation as my Matter over Thread hub during this video, and we'll be issuing voice commands. I'll be using computer as the wait word during this video, rather than the standard wait word, to avoid triggering any of your devices. However, if you are also using computer, you may wish to change it or disable your microphone while viewing. You can also add this device into other ecosystems that support Matter over Thread, like those provided by Google and Apple. This DevLab is divided into 3 steps. In the first step, we'll simply display solid colours on the LEDs and use a button to swap between the two endpoint colours. Currently, you can see the colour of the first endpoint is set to red and displayed. We can change it with a voice command. Computer, set mood 1 to blue.
OK.
Pressing button 0 will switch to displaying the colour set in the second endpoint. Currently it's set to cyan, and we can also change it with a voice command. Computer, set mood 2 to magenta.
OK.
In the second step, we will keep the solid modes in place, but add 2 new modes that will display an animated gradient between the two endpoint colours. Pressing the button again will go to the first of these. Here we have a gradient that goes between the two colours, following the short path around the colour wheel. As the colours I selected are only 60 degrees apart, this is quite a subtle effect. The gradient is animated until all the LEDs are set to one of the endpoint colours and then reverses. This can be seen more clearly if I turn one of the endpoints off to create a monocolour gradient to black. Computer, turn off mood 1.
OK.
The light can be fully turned off by also turning off the second endpoint. Computer, turn off mood 2.
OK.
Let's turn the endpoints on again. Computer, turn on mood 1.
OK.
Computer, turn on mood 2.
OK.
Pressing the button to go to the next gradient mode does exactly the same, but this time takes the long path around the colour wheel from blue set in the first endpoint through cyan, green, yellow, red, and ending at magenta as set in the second endpoint. This is a much more pronounced effect than was seen when in the short path mode. The final stage adds 4 mood light modes that provide a plasma-like effect. If I press the button again, we can see the first of these. To generate this effect, a grayscale coherent noise image is used, and the LEDs take a slice of this image, mapping the 8-bit grayscale values to entries in the gradients we saw previously. In this first mode, we are using the gradient that takes the short path around the colour wheel, creating a subtle effect with the selected colours. Pressing the button again moves us on to the more pronounced gradient that takes the long path around the colour wheel. The animation is achieved by moving the slice up and down within the noise image, and at the top or bottom moving 1 pixel left or right. To reduce repetition, the image width and height are prime numbers. The third mood light mode returns to the short gradient, but this time bounces the slice at a 45-degree angle around the edges of the noise image to generate more movement. The final moonlight mode keeps the 45-degree movement but swaps back to using the long gradient for the most pronounced animation effect. During the video, I'll walk through the code for each of these steps in the Arduino IDE, showing you how to commission the device into the Amazon smart home ecosystem and operate it as we go along. At the end of this video, we'll take a quick look at how I've mounted the components in a commercial enclosure, a Philips 6-watt Moir light that you can easily get hold of. However, in this video I'm using a custom enclosure made from laser cut and etched acrylic. I'll show you how it is put together and share the design files so that if you have access to a laser cutter you can make your own custom enclosure. You'll need some software and hardware to follow along, starting with the Arduino IDE, which can be downloaded from the Arduino website. Once you have the Arduino IDE installed, you'll need to install the Silicon Labs Arduino core into the IDE. There are instructions in the Silicon Labs Arduino core repository on GitHub, and also the Quick Start Arduino Nano Matter video, linked in this video description, walks through the process. The source code for this dev lab can be found in the Silicon Labs Training Examples repository on GitHub. You can clone the repository using your favorite Git client, including GitHub Desktop, or if you prefer you can simply download a zip and unzip it ready for use. This repository contains code for many different training courses. The code for this dev lab can be found in the Dev Lab Arduino Matter Moodlight folder. The README in this folder contains operating instructions and also wiring diagrams. In the Files section, you will find a folder with the code for each step we will take in building the application, plus a fritzing folder with designs for an optional small PCB, and finally an enclosure folder with designs for the custom enclosure I made for this video. In this video, I'll be using the Arduino Nano Matter board with Silicon Labs EFR32MG24 multi-protocol microcontroller that is inside the MGM240S module. This board comes in Arduino's standard nano form factor, and the small board is ideal for incorporating into larger projects. It includes an onboard button and RGB LED, and for further expansion, the majority of pins are brought out to the header holes on the edge of the board. This project is also compatible with the other Matter over Thread boards available for use in the Arduino IDE, including the Silicon Labs XG24 Explorer and Dev kits, and also the SparkFun Thing Plus MGM240p Matter board. The SparkFun board does not have an onboard button, and so you'll need to connect an external button to make use of it. You'll need some WS2812 or compatible RGB LEDs, also known as NeoPixels. If you're not familiar with these, each individual LED can be set to a different colour. You could get a traditional strip like the one shown here, and Adafruit and others also make these in ring shapes with various numbers of LEDs. You can also get strips that provide a neon-like appearance. Be aware that a large number of LEDs can consume a lot of power, particularly the full-size ones like those in strip and ring form, and especially when set to full white. I'll be using some LED rings from Cool Components that are available in a variety of sizes. I'm using 3 rings with 48, 24 and 8 LEDs. The LED data inline should be connected to the D11 pin on the Arduino Nano Matter board. This is the SPI Mozzie line. For power, you can supply 5 volts both to your LEDs and the Arduino Nano Matter board on the in 5V pin, and also connect the ground pins. As a precaution, do not connect both USB and external power at the same time. To wire the other compatible boards, check out the wiring diagrams in the Silicon Labs Training Examples repository on GitHub. These can be found in the README in the project folder. These boards are able to provide some 5-volt power from the board when connected via USB. However, the LEDs can draw a lot of current, so an external supply is still recommended, especially if you have a lot of LEDs in your strip. Finally, you'll need a Matter over Thread hub. I'll be using the Amazon Echo Show 8 3rd generation, but you could use a hub from Google or Apple instead. With the Silicon Labs Arduino core installed, I next need to configure the Arduino IDE to recognize the board type and COM port. This is achieved by using the board drop-down and clicking Select Other Board and Port. Search for Matter in the board search box and select Arduino Nano Matter. If you're using the SparkFun board, that can also be selected here. For the Silicon Labs EFR32MG24 boards, search for XG24 and select the appropriate dev kit or Explorer kit. Next is the COM port selection on the right hand side. At the moment my board is not connected. If I connect the USB lead, I can see which port appears and select it. When happy with the selection, click the OK button. Then I need to check the protocol stack that will be used from the Tools menu. For this video I will select the Matter entry. If you want to create Bluetooth only applications, select BLE. And for applications where you are not using the radio, select None. By only selecting the radio protocols you need for your application, you can speed up compilation and free flash and RAM memory for your application, as this removes unused libraries. Next, we'll select the programmer for use with the board. From the Tools menu, click the Programmer entry. For the Silicon Labs and SparkFun boards, select Simplicity Commander. For the Arduino Nano Matter board that I'm using today, select Open OCD. We can now program an appropriate bootloader for Matter applications from the Tools menu by selecting Burn Bootloader. Burning the bootloader also erases the whole flash, including any Matter credentials that are stored there. If you are reprogramming a board with different device type software, it is a good idea to do this and also remove the device from the ecosystem you have been using. This ensures that on recommissioning, the new device type is properly recognized. Let's start with the first step, which is mainly concerned with making sure the Matter device is set up correctly, ensuring it can join a network and that the two color bulb endpoints can be used to change the two colors in the device. We'll have two modes, selected with a button press, that swap the LEDs between the first and second endpoint colors. I have the moody_1_solid.ino file open from the Step 1 folder. This is based upon the Matter color bulb example, which only has a single color bulb endpoint. I've adapted the example to add a second endpoint so two colors can be set, and it uses button presses to cycle between the colors set in each of those endpoints. It also sets things up for the later steps of the Dev Lab by bringing in a fast converter from the hue, saturation and value color space to the red, green and blue color space. While there is a converter in the Silicon Labs Arduino core libraries, it uses float values which are slow. Especially for the number of conversions this application will need to perform in building gradients. This fast converter uses integers, sacrificing some accuracy for speed. On the website, there is a large description of how it works and minimizes errors while still producing fast results. Let's work through the Step 1 code. First, we have includes taken from the libraries for Common Matter APIs and Matter Lightbulb APIs, plus the header for the WS2812 RGB LED driver that's provided as part of the Silicon Labs Arduino core. Next, we have includes from the application folder, which is just the fast HSV to RGB converter in this step. Then we move on to hash defines. First is the option to boost saturation in a bulb. You might want to do this if you're using the color wheel in the Google Home mobile app, where colors at the edge of the wheel are only 80% saturated. Voice commands, however, will fully saturate. If you're going to make a lot of use of Google Home's colour wheel, setting a value of 51 here will result in fully saturated colours when selected from the edge of the colour wheel. Next is the bulb count. This is the number of bulb endpoints and hence different colours that appear in the device. As we will be creating a gradient between these two colours, it should be left as is, unless you want to add your own code to mix 3 or more colours together. Following this is the pixel count define, which specifies how many RGB LEDs are to be controlled by the application. Adjust this to match how many LEDs you have attached to your device. Then we have defines specifying the pins for the onboard LED used to indicate the current mode and the button to change the mode, together with the button logic level when it is pressed. The final set of defines are for the mode values and a count of the available modes. Then we move on to global data variables within the application, beginning with a value to hold the current time in milliseconds for timing the various application tasks, followed by variables for handling the digital I/O used for the LED and button. There are values for timings here. The app will poll the button and update the LED every 100 milliseconds. The LED bit variable is cycled 1 bit at a time to produce different flashing effects whilst the device is in a network. Finally, the button state variable holds the most recently read state of the button. Then we have data for the Matter bulb endpoints, starting with 2 instances of the Matter color light bulb object. Next, we have a set of variables to hold the on-off state and HSV color components for the bulbs. These are initialized here with default settings to be applied when the application starts to run. There are also RGB color values for each bulb. These will be calculated from the HSV values each time a bulb's color is changed. Finally, we have timing variables for the bulbs. These will poll for changes sent via the Matter network and apply them to our device. The final set of variables are for the RGB LEDs, beginning with the object for driving them. Next, we have the current display mode that will be cycled with a button press, together with bit masks for the flashing pattern that will be shown on the onboard LED to indicate the current mode. Once again, we have timer variables to control when the RGB LEDs are updated. Then there are the prototypes for the functions implemented in the .ino file. We'll look at these as we go through the code. The setup function is called once during startup. This application will stay in the setup function until the device is commissioned and connected to a Matter network. It starts by initializing an LED state variable. This will be used to toggle the onboard LED while waiting for commissioning and connection to be completed. The serial port is initialized and you will find debug messages being output throughout the code. The onboard LED is initialized and turned on. Also, the button is configured and the initial state is read to check for changes later. Next, Matter and the 2 Matter bulbs are initialized. The default state and hue, saturation and value colors from the global application variables are applied to the data held in the Matter bulb objects. Those default colors are then converted into red, green and blue, ready to be displayed. The RGB LEDs are initialized and set to dim magenta while the application waits to be commissioned into a Matter network. When writing data to these LEDs, interrupts are disabled as the WS2812 protocol needs to be timed precisely. Next, a check is made to see if the device has not already been commissioned into the Matter network. In this case, the data needed to commission the device is output to the serial port. Then, the code waits for the device to be commissioned by sitting in a loop, toggling the onboard LED on and off. The commission state of the device is held in non-volatile memory. If the device has been previously commissioned, it will simply skip over this code. It does not need to be recommissioned each time it is power cycled. Next, the RGB LEDs are set to dim yellow while awaiting connection to the Matter network. This is followed by similar code to commissioning that will loop and flash the onboard LED until the device is connected or reconnected. Once connected, the colour is changed to dim cyan, while the device waits for the bulb devices to become online in the network and so controllable from a hub device. When online, the onboard LED is turned off and the timer values that will be used in the loop function are initialized. Then we move on to the loop function, which is called repeatedly while the application runs and contains the main processing for the running connected application. It begins by reading the current time in milliseconds, which will be compared against the time values for the various tasks that are to be performed regularly. When the bulb timer fires, the timer is restarted. The status of the Matter bulb objects are read. We'll look at the read bulbs function in a moment. The digital I/O timer is checked next and is restarted when it fires. In here, the button is read first, and if its value has changed since the previous iteration, the display mode is cycled. Next, the onboard LED is handled. If the current bit in the LED bit mask is set, then the LED is turned on. Otherwise, it is turned off. The LED bit is then shifted for the next iteration. This allows different flashing patterns, controlled by a bit mask, to be displayed on the onboard LED. The bit is also checked just before updating the LED. If no bits are set, it is restarted by setting bit 0. The final processing in the loop function takes place when the pixel timer fires. It simply calls the write pixels function to output data to the RGB LEDs, depending on the mode. Then there are 3 helper functions. The first is read bulbs. This loops through the Matter color bulb objects, checking to see whether the on-off state or HSV color of each bulb has changed since the previous call. If there is a change, the HSV color is converted to the RGB color space, ready to be displayed. When the bulb state is off, black is used to override the set HSV color. This function returns a Boolean, indicating whether an update has taken place. In this step it is not used, but it is in place ready to use in the next step. The second helper function, write pixels, outputs the data to display appropriate colors on the RGB LEDs, depending on the selected mode. When in the solid 0 mode, all pixels are set to the color of the first Matter color bulb object, using its already calculated RGB values. Similar code is used in the solid 1 mode to set the RGB LEDs to the color of the second Matter color bulb. The final function, fast HSV to RGB, is a wrapper around the fast HSV to RGB 32-bit function. It limits the passed in hue to values between 0 and 359, as this application and the Matter color bulb object define the hue in this range. It then scales the hue up into the units used by the conversion function, and finally converts to RGB values. In the Arduino IDE, the application can be compiled and uploaded by clicking the Upload button. Opening the serial monitor and then resetting the board allows me to copy the URL for the QR code used to commission the device, which I can then paste into my browser. I'm now ready to commission the device into my Matter network. We can see it is not yet in a network by the regular flashing of the onboard LED, and that it is waiting to be commissioned by all the RGB LEDs being set to dim magenta. To commission the device into my Amazon network, I need to use the app on my mobile phone. Begin by going to the Devices tab, Then click the Add button in the upper right corner and select Add Device. Scroll down to the bottom of the list of devices and then select Other. On the next screen, select Matter. Confirm that the device has a Matter logo and also that it is turned on. Next, select Scan QR Code and scan in the code from your browser window to begin commissioning. We saw the colour change to dim yellow when the device was commissioned and waiting for connection. Then dim cyan when connected and waiting to come online. Finally, it changed to blue when it came online, which is the default colour for the first bulb contained in the device, which is currently being displayed. I now need to complete the setup in the ecosystem by clicking Next. Even though we have a single physical device, 3 logical devices have been discovered. The one named First device acts as a hub for the 2 colour light devices, currently named First Light and Second Light. This hub does not provide any functionality. It is merely a container for the light devices. This is a side effect of creating the light endpoints at runtime. Let's set up each of these logical devices, starting with the hub. I'm first prompted to rename the device. I'm going to rename it to Mood Hub. Next, I'll set up the first light device. I'll rename it to Mood 1, and I'll also add it to the mood group that I already created. I'll repeat the process with the second light, this time naming it Mood 2. I'll also add it to the mood group. By placing the 2 light devices into the same group, I'll be able to turn them on and off together by issuing commands to the group. The device is in mode 1, indicated by the single brief flash of the onboard LED. I can use voice commands to change the colour. Computer, set mood 1 to green.
Okay.
And I can also turn it off. Computer, turn off mood 1.
Okay.
And also back on again. Computer, turn on mood 1.
Okay.
If I press the onboard button, I can swap to mode 2, which displays the colour of the second light, currently magenta. This is indicated by a double flash of the LED. Computer, set mood 2 to cyan.
Okay.
And that concludes step 1, where we have set up a single matter device containing 2 lights which can be individually controlled, and the button is used to swap the output between the 2 light devices. In the second step, we will add an animated colour gradient between the 2 selected colours. I have the moody2 gradient.ino file open in the Arduino IDE for this step. We will calculate 2 different gradients and add 2 new display mode, one for each gradient. The first follows the short path around a U colour wheel. So if the selected colours are green and blue, it will start at green, take in cyan before ending up at blue. The long path goes the other way around the colour wheel. So in this case, it would start at green, take in yellow and red, passing through magenta before ending up at blue. And we need to take care when calculating this gradient when we pass the 0 point at red. The changes begin by defining the number of entries in the gradient that will be created. In the next step, I'll be using an 8-bit grayscale image to produce the plasma effect. So the gradients will be sized to 256 entries, one for each level of grey. Then we add 2 new display mode defines, one to display the short route around the colour wheel and one for the long route. The mode count define is also updated. For global data, there are arrays to hold the RGB gradient values for both the short and long paths. A variable is used as an index into the gradient being displayed. This is updated each iteration for an animated effect. A boolean is used to track whether the index is being incremented or decremented to allow the animation to work forwards and backwards through the gradient. The default display mode is updated to the first of the new gradient modes, and new onboard LED flashing sequences are added for these new modes. In the setup function, a call is made to a new write gradients function after initializing the matter bulb object. This function will calculate the gradients between the two set bulb colors, and we'll take a look at it in a second. In the loop function, there is another call to write gradients whenever read bulbs indicates that the on-off state or color of a bulb has been changed in order to update the gradients. Let's see how the write gradients function works. It begins by taking local copies of the HSV colors set in the two bulb endpoints. These may need to be manipulated if a bulb is off or fully desaturated to avoid mixing in the hue of the endpoint that is not displaying any color while the gradients are calculated. There are a few other local variables that are used to hold intermediate results. Hue values for the short path around the color wheel are calculated. Hue values may be adjusted here to be larger than 360 degrees, where the gradient would otherwise need to cross the 0 point at red. The HSV to RGB conversion function will bring such values back into range before converting. This allows simple scaling to be applied to these adjusted hues when calculating gradient values. Similar code is used to adjust hue values for the long path around the color wheel. Then there is a check to see if both bulbs are turned off. In this case, the value component is set to 0, so black is used throughout the gradient. Next, if bulb 0 is off while bulb 1 is on, the value component of bulb 0 is set to 0 for black. The saturation and hue components from bulb 1 are copied into bulb 0. This avoids mixing the hue and saturation of bulb 0, which is off, into the gradient, resulting in a single color dimming to black for the off bulb. Similar code is used for when bulb 1 is off, but bulb 0 is on. When both bulbs are on, a check is made to see if one of the bulbs is fully desaturated. In this case, the hues of the bulb that has color is copied into the desaturated bulb to avoid mixing the hue of the desaturated color into the gradients. Once all the adjustments have taken place for the colors at the end of the gradient, the individual colors that form the gradient are calculated using the map function, which is used to scale between the two HSV colors, and then the fast HSV to RGB function converts to the RGB values in the global gradient arrays. To display the gradient on the RGB LEDs, the write pixels function is updated, beginning with some local variables used to output the colors to the LEDs. Then we have the case statement for displaying the short gradient. The global gradient index and direction variables are copied into the local variables as a starting point for the lookups before looping through the pixels. When looping through the pixels, some checks are made to ensure all pixels are set to the selected colors at the ends of the animation, instead of just using the single pixel with that color from the gradient arrays. At the start, the RGB color from the start of the gradient is used, and at the end of the animation, the RGB color from the end of the gradient is applied to all the pixels. In between those two endpoints, the RGB color is taken directly from the gradient arrays at the appropriate index. Then, the color of the pixel is set to the calculated values. The local variables for the index and direction are updated ready for the pixel, reversing the direction if required. Upon exiting the loop through the pixels, the global variables for the index and direction are updated ready for the next call to the loop function. This is followed by the case statement for displaying the long gradient. This is exactly the same as the short gradient, it just uses values from the long gradient RGB arrays instead of the short gradient RGB arrays. In the Arduino IDE, the application can be compiled and uploaded by clicking the Upload button. Note that I have not reflashed the bootloader this time to retain the Matter credentials in non-volatile memory, as the device type is unchanged. After the firmware is flashed, the board reboots. This time it will skip the commissioning stage, so we won't see the LEDs going to the dim magenta colour. Instead, we will see dim yellow as it reconnects, followed by dim cyan as it waits to be queried by the hub. The time taken to come online will depend on your hub and may be a few minutes. Once online, it will begin displaying the short gradient mode, indicated by a triple flash of the onboard LED. The default colours in this mode will cycle from blue through to magenta and back again. Pressing the button will switch to the long gradient mode, indicated by quadruple flashes of the onboard LED. The long path will cycle from blue through cyan, green, yellow and red to magenta and then back again. If I change the colour of one of the bulbs, computer, set mood 2 to green.
OK.
New gradients are recalculated and displayed. If I turn off a bulb, computer, turn off mood 1.
OK.
We can see the gradient running from the green colour of mood 2 to black without mixing in any of the colours set for mood 2. Similarly, if I set a bulb to white, computer, set mood 1 to white.
OK.
We can see a similar effect with the desaturated colour. In this third and final step, we will add more modes to display some coherent noise that will appear as a plasma-like effect. Using the short and long gradients, combined with fast and slow animation, will result in 4 new modes. To generate the noise, I'm going to use the Fast Noise Light web interface. The default settings you can see on my screen produce some fairly uniform noise using the Open Simplex 2 noise type. I prefer a slightly more pronounced effect that can be achieved by selecting Ridged from the Fractal drop-down. Where the image is black, the colour at the start of the gradient will be displayed, and where it is white, the colour at the end will be used. As you can see, there are very few areas at these extremes, and those are the colour the user selects, so we want to increase their visibility. On the Preview Settings tab, the black and white points can be adjusted. Setting the black point to -0.6 will exaggerate the blacks, while setting the white point to 0.7 will exaggerate the whites, while still leaving a nice grayscale gradient in between. The final setting to adjust is the size, as the 768 pixel square is a bit large, so I'm going to reduce it to 479 pixels wide by 269 pixels high. This is large enough for what we want to display. We should now be able to save this as a bitmap image, but I found that I'm unable to open the image to convert to a C array. So in order to get the image, I made a screen capture of the window and cropped and saved it to a PNG file in a graphics editor. To animate the plasma effect, I'm going to take a slice from this image. The width of the slice will match the number of pixels, and the height will be 1 pixel. For animation, I'm going to move it around the image in each iteration of the loop function. For the slow modes, I'm going to move it up and down and then shift it 1 pixel left or right when at the top or bottom of the image. This will result in colour moving across the LED strip where there are diagonals of white in the source image. For the fast mode, I'm going to bounce it around the sides of the image at a 45 degrees angle. This will exaggerate the movement where there are white diagonals and also introduce movement where there are white verticals. To minimise repetition, the dimensions I chose for the image, 479 by 269 pixels, are prime numbers. To convert the image to a C array, it can be loaded into a file to C array converter. Setting the palette to 8-bit grayscale, unchecking static, and selecting uint8 as the data type, then finally deselecting the progmem option, allows the convert button to be clicked to generate the C code and allow it to be saved as a C header file for use in the application. With the moody3 noise.ino file open in the Arduino IDE from the Step 3 folder, the noise image is brought into the application by including the header file we just generated, and defines are added for the new noise modes, plus the count of modes is increased to match. And then there are some global variables to index into the noise image, starting with the row and column, and followed by flags to indicate whether they are being incremented or decremented. Finally, for the global data, the default mode is updated to the slow, short noise mode, and new LED flashing patterns are added. The remaining code changes are in the write pixels function. Let's take a look at the short slow animation, which begins by calculating the initial index into the noise image array for the first LED. It then loops through the pixels, looking up RGB values from the short gradient arrays, and taking the index into the gradient from the noise image array for the pixel. Once all the RGB pixels have been updated, the row and column values are updated ready for the next iteration. When in the first row of the image, the row direction is reversed, and the current column is moved one step left or right, depending upon the current column direction. The column direction is also reversed here when the slice is at the left or right edge of the image. Similar edge case handling is used when on the bottom row of the image. After dealing with the edge cases, the row for the next iteration is then updated depending on the current row direction. The code for the slow long animation is exactly the same, but the color values are taken from the long gradient arrays. For the two fast noise modes, the code is similar, except the current row and column are updated to move the slice at 45 degrees around the edge of the image. In the Arduino IDE, the application can be compiled and uploaded by clicking the Upload button. Just like in Step 2, it will reconnect to the Matter network using data from non-volatile memory. When the mood light comes online, it defaults to the slow, short noise mode, slowly animating the noise image with the short gradient between blue and magenta. This noise mode is indicated by the onboard LED being on, with a single brief off period. As the colours are close together, this is quite a subtle effect. Pressing the button will move on to the slow, long noise effect. Double off periods on the LED indicate this mode. With the long gradient taking in so many colours, the effect is more pronounced. Next, we can move on to the fast short effect, indicated by triple off periods on the LED. While the gradient is still short, the movement is more pronounced due to the faster movement of the noise array. Let's change a colour. Computer, set mood 1 to red.
Okay.
The final mode is the fast long effect. This time indicated by quadruple off periods on the LED. As the gradient is long and the slice is moving quickly around the noise image, this is the most pronounced effect. Turning off one of the bulbs, computer, turn off mood 2.
Okay.
Will display a single colour plasma effect fading down to black. Finally, to completely turn off the LEDs, I can set the other bulb to off as well. Computer, turn off mood 1.
Okay.
Before I wrap up this devlab, I thought it would be a good idea to take a look at further enhancements that could be made to the application. The first obvious enhancement is to experiment with the noise image used to generate the plasma effects. As you may have noticed, the fast mode, taking the long route round the colour wheel, isn't really a relaxing effect. One way to calm it down would be to reduce the frequency in the general noise settings to make the image less busy. Reducing the fractal octaves to 2 or lower also creates a simpler image for a more subtle effect. You can also experiment with the other settings to generate different noise images and even have multiple images in the application with additional modes to switch to them. Since recording the earlier parts of this video, I've generated a header for the more subtle noise image, and updated code that uses it can be found in the Moody 4 Final folder in the GitHub files. The original busier image can be enabled by adjusting the comment markers to restore noise.h and remove noise subtle.h. I also added a few more tweaks to this version of the software. The first is this wait online #define. Setting this to false will allow the software to exit the setup function before it is commissioned, connected and online in a network, and so start displaying the mood light effect immediately. This is mainly intended for use when experimenting with noise images, so you can immediately see the effects of your changes without waiting for the device to come online. You can still commission the device and it will still rejoin. There just won't be any visual indication via the LEDs when it does become available. And of course, you won't be able to interact with the device remotely during this time. The other addition is the option to factory reset by holding down the button for 5 seconds at power on or reset. During the 5 seconds, the LEDs will display dim red, and when the timer runs out, if the button is still down, the non-volatile memory containing the Matter credentials will be erased, allowing the device to be recommissioned into a new network without programming the bootloader and application again. You should also remove the device from the ecosystem it was previously a member of. Note that if the device was not previously commissioned, this is skipped and you will not see the red indication. One final modification that I've not implemented and is left as an exercise for the viewer is to add support for a matrix of LEDs instead of a strip, as handling this layout of LEDs doesn't look good when it's treated as a strip. To support this, a rectangle instead of a strip will need to be taken from the noise image and moved around. If you take this route, be aware that it is normal in these types of devices for the LEDs to be ordered in a zigzag fashion, going forwards then backwards as you move down the rows. So this will need to be taken into account when updating code. On the hardware side, I've made a custom PCB for use with my enclosure, even though only 3 connections are required. The PCB allows a barrel jack socket to be mounted to provide power. This particular socket uses narrow pins that are compatible with a breadboard. It also has header pins for ground, 5 volts, and the data line to the WS2812 LEDs. There is an extra pin on this header for the TX nano pin, which can also be used to drive a second set of LEDs. In this configuration, I've mounted them on the bottom of the board so it can be suspended within my enclosure. But they can alternatively be mounted on the top of the board to allow it to sit flat, though you will need to not fit the center header sockets and pins for the Arduino in order to leave the power socket exposed. For use in other projects, I2C pins are brought out to a second header along with 3.3 volts, or these could just be used as general digital or analog inputs and outputs. Note, there are no pull-up resistors here for I2C. Lots of breakout boards have their own resistors, and if not, you'll need to add some. There are also holes to mount a button and a resistor if you want an extra input. Finally, there are holes I added for another GPIO and ground. These are intended to mount a small piezo buzzer, but you could make use of them however you want. If you want to make this PCB, you can find a fritzing file in the fritzing folder downloaded from GitHub, where you can view the PCB, schematic and breadboard layout. There is also a zip file containing the Gerbers. For an enclosure, I've successfully used a Philips Moire 6-watt light to diffuse the bright LEDs. These are available in both cool and warm white versions, and both use the same enclosure. Inside, the LED rings from Cool Components feature small holes which allow mounting using M2 nylon standoffs, and holes on the rear allow wires to be run, providing power and data to the LEDs. To build the custom enclosure, I've used 2 sheets of 3mm opal frost acrylic, cut and etched using a laser cutter. Holes allow the wiring to be cable tied to the rear of the bottom panel, and M3 standoffs attached through rubber feet. On the front of the bottom panel, the LED rings are also attached using cable ties, and slots for mounting the nanoboard in a hidden way are also available. On the top panel, the logo and text are etched into the bottom side, leaving a smooth surface on top. The slots allow the nanoboard to be plugged into the PCB to mount it. The M3 nylon standoffs from the bottom panel allow the top to be fixed in place. With the PCB suspended below the top panel, the WS2812 wiring can be connected and power provided via the barrel jack. The nanoboard remains visible with the button accessible. In the enclosure folder downloaded from GitHub, you will find SVG files that can be imported into laser cutter software for use, and also Lightburn files, which is the software I used, though you may need to experiment with the settings to get a clear cut and etching. So that brings us to the end of this dev lab. We started by being able to switch between 2 solid colours. Then in the next step we added gradient displays to gradually change from one colour to the next. And in the final step we added a mood light effect using a generated coherent noise image. Don't forget there are links to all the resources used in this video in the video description. Thanks for watching. Computer, turn off mood.
Okay.